Hello there, Mr. Sutton here, bringing you the AB Calculus 3.3 lesson on differentiability, part 2. In this one, we're going to figure out if a piecewise function is differentiable, and we'll find missing constants that make a piecewise function differentiable. For a warm-up on this one, this is going to be a two-parter. First warm-up, if I want to show that f of x, this piecewise function down here, is differentiable at x equals 1, what do I need to prove? And we really do need to show this because this is a piecewise function, so we might have some kind of weird continuity slope issue at this border value. So pause the video and see if you can remember about what differentiability means. So there's two parts to this. First part, we need to show we are continuous at x equals 1, which means we need to show that the function actually exists there, that the limit exists there, and that the limit as we approach 1 and the function value at 1 are actually going to be the same number. So we have to show all of that. Next, we have to show that the slope limit exists, which is to say the limit as x approaches 1 from the left of f prime and the limit as x approaches 1 from the right of f prime both equal the same number. All right, so for the second warm-up here, go ahead and show all that. Determine if f of x here is differentiable at x equals 1. Okay, let's see how that went. So first we do the continuity piece of it. So we do left, right, center. We have the limit as x approaches 1 from the left of the original function. That's just going to be 1 plugged into x, which is just 1. Right side limit, we're plugging 1 into this lower function here. 1 over 1 still gives us 1. And we always have to mention the function value. F of 1 happens to be the same as the left side limit, so it also equals 1. So we've shown that our limit as x approaches 1 and f of 1 are the same thing. So that means that we are continuous at x equals 1. But we wanted differentiability. Continuity by itself not necessarily enough, because a cusp is continuous but not differentiable. So doing the slope limit piece now, let's take the limit as x approaches 1 from the left of f prime. So that's going to be the derivative. First off, we have to take the derivative of this x here, which is just 1. And if you plug 1 into 1, you just still get 1. So that f prime left side limit is 1. Now taking the derivative from the right side here of this lower rule, well, this is initially x to the negative 1, whose derivative is negative x to the negative 2. So we want the limit as x approaches 1, this should say from the right here. Oh, actually it does, it's just the plus is kind of faint. Limit as x approaches 1 from the right of negative x to the negative 2. So this is just actually going to be negative 1 when we plug it in. And we see here that the left side limit and the right side limit of f prime do not match up. Since we failed the second part of our test, we're going to say that our function is not differentiable at x equals 1. For this next example, we want to figure out if this function is differentiable at x equals 2, and if it is, and only if it is, try to find f prime of 2. So pause the video, give it a shot. All right, so let's see how the continuity piece of this went. We have the left side limit of our f of x function. That's going to be 2 plugged into this first rule here. So 2 times 2 minus 4 is 0. Now the right side limit, we've got 2 squared minus 2 times 2, still 0. And we always have to show the f of c, so f of 2 is going to correspond to this first rule here, again giving us 0. We see that limit as x approaches 2 and f of 2 match up. So again, our function is continuous, this time at x equals 2. So we try the slope limits now. Limit of the slope as we come from the left, f prime of this first rule here is just going to be 2, no matter what we plug into it. And as we come from the right side now, we're doing f prime of x squared minus 2x. So the right side limit, that's going to be the limit of 2x minus 2 as x approaches 2 from the right. 2 times 2 is 4, minus 2 is 2. So that actually matches up with what we have for our left side f prime limit. Since those limits match, which I have to write out explicitly here, since those match, that means that my function is differentiable at x equals 2. Now, actually finding f prime of 2, we're just going to use f prime of whichever rule the c value, 2 in this case, was part of. So I look up here in my original function, and it looks like 2 is part of this first rule. So we'll just take the derivative of this first rule, which should match the second rule. So that's just going to be f prime of 2 equaling 2. For this last example, we're given another piecewise function, and this one you might notice has these mystery constants a and b in it that we will now try to find values of that make this piecewise function differentiable at x equals 1. So we're basically going to try to force continuity and differentiability, pretty much pretend we're testing for them, and then we're going to get some equations that we can solve for a and b. So let's start by forcing continuity. So we'll run our continuity test. Actually, take a moment, pause the video, and test continuity on this thing and see what happens. All right, so if we're testing this, we need the left side limit at 1. So as we approach 1 from the left, we're using this first rule. 3 times 1 squared is 3. And now we need the right side limit at 1. So we're using the second rule here. A times 1 plus b is just going to be a plus b. And we don't know what a and b are, so that's actually all we can write for that one. And now we're doing continuity, so we also have to look at f of 1. F of 1 corresponds to this first rule here, because we have x equals 1 in that interval. So that's going to be 3 times 1 squared, which is, again, 3. So if this function is actually differentiable, that means it must be continuous. So that means all three of these things need to match up. So that means that 3 must have a value of a plus b. Okay, well, we don't know enough to actually solve for a and b yet, so we're going to keep going. We're going to now force differentiability, force the slope limits really is what we're doing here. So we need to take the limit of f prime from the left and right. Pause the video and take a moment to do that. So the left side limit of f prime, that's taking the derivative of this first rule. That's going to be 6x, and we're still taking the limit as x approaches 1 on this. So if I plug 1 in for x, that's just 6. And now let me take my right side limit of f prime. That's going to be using this bottom rule and taking this derivative. Remember that a and b are constants, so this b gets differentiated away. The derivative of ax is just going to be a, so that's just going to be a for that right side limit. So now, since these limits have to match up for differentiability, we can write the equation 6 equals a, basically left equals right. And this actually gives us information that we can solve this first equation with now. Instead of writing 3 equals a plus b, I can write 3 equals 6 plus b. Subtracting 6 gives me a b value of -3. So as we head into the wrap-up, you may have noticed we didn't have any examples where we failed the continuity test in the beginning. You always have to do it, but you may wonder if you really need to. Well, let's say that Isaac wants to skip that part of the differentiability test and just do the derivative limit test. See if you can pause the video and write or draw a function that would pass the derivative limit test but fail the continuity test. All right, so some examples I came up with. We have parallel lines like in the function absolute value of x over x, which looks like this. You're approaching the same slope from the left and the right as you get closer to 0, but clearly there's a discontinuity here, a jump discontinuity, which means we would not actually be differentiable. Another neat little example is if you have a hole, like in this function right here, where if you graph this out, and I drew the hole in here, but yeah, you have a hole, so you're not differentiable there. So you always have to check continuity before moving on to the slope limit test. So this concludes differentiability part 2. Till next time, Mr. Sutton signing off.